Good afternoon, good morning, good evening to everybody. My name is Alfio Quarteroni. I'm the MOX director. And today at our MOX Colloquium, we have the pleasure to host Professor Siddhartha MISHRA. Professor MISHRA is currently a professor for applied mathematics at the ETH, the famous Federal Institute of Technology in Zurich, in Switzerland. Siddhartha received his PhD degree in mathematics in 2005 at the Indian Institute of Science and Technology, of Science and the Tata Institute of Fundamental Research at Bangalore in India. His interest in research are mostly the areas of numerical analysis, computational science, nonlinear partial differential equations, and the computational fluid and plasma dynamics and computational geosciences, and more recently in machine learning. So his work has been recognized by many awards and honors, and these include 2 ERC grants, a starting grant in 2012 and a consolidator grant in 2017. Then the Richard from Mises Prize in 2015, the Jacques Williams Medal in 2018, the Collas Prize in 2019, and the Infosys Prize in 2019. Professor MISHRA has also been invited as a speaker at the International Congress of Mathematicians in 2018 in Rio de Janeiro. Today, Professor MISHRA will talk on a very interesting and I would say hot topic. The title of his talk is Deep Learning and Computations of High-Dimensional Partial Differential Equations. Sid, thank you very much for accepting to talk at our MOX Colloquium. The virtual floor is yours. Thank you.
First of all, thank you so much, Alfio, for this very kind introduction. And thank you and Luca and Christian for the invitation. It's really a pleasure to talk to people in Milan and from elsewhere. It's a pity that it's not a real event because I could have easily gone to Milan from Zurich, but we live in strange times. So we have to take this with a pinch of salt. Anyway, so I start with, let's see if I can, okay, sorry. So as I said, my title is about machine learning and PDEs. So all of you know what PDEs are, partial differential equations. In particular, they model natural phenomena in physics, in engineering, in the sciences, all the way from the subatomic, from the electronic scale, through the Schrodinger's equation, to the cosmic, to the universal scale, through the Einstein equations, and everything in between. And we all know that in the last 50, 60, 70 years, there are some extremely successful numerical methods, finite elements, finite differences, finite volumes, and so on, to numerically approximate or simulate these equations. Actually, Alfio, Professor Quattroni, is one of the leading experts in the world, and one can learn everything about these methods from his books, as I did in many years back. But nevertheless, the point is we are reaching a place where it is the limits of some of these methods are getting more and more apparent, right? And among the various limitations, one particular one is computations in high dimensions. And by that, I mean dimensions which are greater than 4, because 4 is sort of space and time, that's our physical world. But anything more than that, it gets complicated. But what does this high dimensionality mean, right? So there are 2 ways to think about it. One is when the problem itself, the PDE itself, sort of the space in which it is set is high dimensional. These are what are called explicitly high dimensional PDEs. From physics, you can think of the Boltzmann equation, which is 7-dimensional, the radiative transfer equations, which are 7-dimensional, Black-Scholes, Schrodinger's equations. These are in hundreds of thousands of tens of thousands of dimensions, right? So where the physical space itself is high dimensional. But there's another very large class of problems where the dimensionality, high dimensionality, is implicit. And these are what are called parametric PDEs. And let me start with that. And let me give an example. Uncertainty quantification, which is a very important thing in engineering. The objective is not to compute just one realization of your flow. So this is, for instance, a single realization of a turbulent compressible flow. But this single realization does not give us a lot of information. What we're interested is in statistics, for instance, the mean and the variance and more complicated statistics. And the point is that when you compute the mean and the variance, the most obvious way is to take a lot of simulations, a lot of samples, and average them in some manner, right? And the point is, even for a single simulation with fairly state-of-the-art code, what you get is on one of the biggest machines, certainly in Europe, but in the world, it's 12th at the moment. It was 6th when these computations were done. For a single run at 1024 cube, so this is about 10 billion degrees of freedom, it took 280 node hours. Okay, this is some number. But the point is, a single run, as I said, is not enough. You have to do statistics. And then you have to do 500 or 1,000 of these runs. And then if you start putting a value on it, dollar value or Swiss franc value on it, then the simulation on a true cost basis costs 700,000 US dollars or Swiss francs, 650,000 euros. Think of the currency that you like. So this is an extremely large sum of money for a single simulation, single uncertainty quantification. And this is more and more generic these days. These kind of runs are going to be more and more routine, and they are going to be very, very expensive because you have to call a very expensive solver multiple times. So this is what happens in what are called many query problems, where the solver is called again and again and again. Another classic example is in design problems. Alfio has worked a lot on that, but the basic idea is that you, for instance, just take an airfoil for illustrative purposes, and I want to design an airfoil, to, let's say, minimize the drag while keeping the lift constant, and I want to change the shape to ensure that, right? And to do so, I parameterize my shape in terms of, 20 to 50 parameters, what are called hex-Henne functions. And then I choose or optimize using some standard optimization algorithm. Again, I have to call the PDE solver. This one is not going to cost 700,000 Swiss francs, but still expensive, multiple times. And this is what the main point is, that multiple calls to PDE solvers can be very, very expensive. So these kind of problems I can abstractize and write them in a more mathematical form in the following manner. Okay, let's focus a little bit on this. So of course, my solution is a function of space, which could be three-dimensional, time, certainly one-dimensional, and then a parameter. And these parameters, they represent, for instance, the probability space in this uncertainty quantification problems, or they could represent the design space, for instance, in an optimal control, PDE constraint optimization problem, and so on. So now the differential operator, on the other hand, does not involve the parameter, as it should not. This is a function of space and time, and you've been given some input. And the key point here is that your space and time could be 3 + 1 dimensions, but your parameter lives in a very high dimensional space. So this could be 100,000 dimensional or whatever. It could be anything more than 10 to 100 dimensions. So this is a large dimensional space. And what you're interested in is the solution field as a function of space, time, and parameters. Or many times the object of interest is a functional, for instance, an observable like the lift and the drag, which is a function of the parameters, because somehow you integrate out the role of space and time. And as I said, computing these things as a function of parameters is very expensive because of the context that I just explained. So what we are going to do is we are going to approximate these fields or these observables with deep neural networks. These are functions. Deep neural networks are very powerful approximators of functions, and we are going to approximate them as a surrogate with the view that now our cost will be dramatically reduced. Let's see if we can do that. But before that, deep neural networks, these days, these are sort of the mainstay of machine learning, so everyone knows it. But just for the sake of notation, let me tell you what these are. So for my purposes, these are just functions. Functions means given an input, they will give me an output. The input could be a high dimensional vector. Remember that this y is, this y lives in a very high dimensional space. So the input could be a high dimensional vector. And I pass this vector through several layers, so what are called layers, but these are nothing but compositions. So it's a function which is built out of compositions of simpler functions. And the simpler functions are either affine. So you see this is the linear part, there's a matrix multiplying a vector, and then the affinity comes from the fact that we have another vector here, so-called bias. And this linear part or affine part is then composed with an activation. Activation is just a scalar nonlinearity. So this is standard. So you start with the input, then you put it through an affine layer, which is this affine function, and then through a scalar nonlinearity, affine scalar nonlinearity, affine scalar, and so on. And you do this multiple times. So this is the key to deep neural networks, at least. And the idea is that you're going to remember that we want to learn functions, right? So this was the objective, that we wanted to learn either the fields or the observables, the functions with appropriate input and output spaces. So let me call this ground truth as L. I'm going to approximate this by this construction here. But of course, to do so, I need to tune, or I need to train the parameters of my neural network, which are the weights and the biases. I club them together in a single number called theta, and then have been given some data. Means you learn from data, right? So you've been given some realizations of this function. These realizations, for instance, could be on a randomly chosen set, IID randomly chosen set, so-called training set. And then I want to minimize the mismatch, the so-called loss function. So this is the output of the neural network on this training set. This is your given data, which you know. And you want to minimize this to find the best fit in the class of theta. So this is it. So you have data, you have a certain architecture of your neural network, and you use some, this is a very high dimensional non-convex optimization problem. So one uses some variant of the stochastic gradient descent method or PFGS or something, and you find the minimizer. So at the level of actually coding this up, this is in a way trivial. You can do it with TensorFlow, with PyTorch, with all the numerous software that is available for these purposes. But the question is, can this be done? Okay, in principle, you can do it, but does it lead to anything useful? In other words, the question is, for a given tolerance, remember I was interested in the observable or in the solution field, for a given tolerance, can I find a neural network such that the difference between this is small? It's up to some tolerance. The answer is yes. Why? Because as long as this map here is even measurable, so not just continuous, but much integrable, much, let's say, irregular than that, there is something, neural networks have something called universal approximation property, that if you have been given any function which is measurable, you can always find a neural network which is going to approximate to high precision. That's very nice, right? However, this is why there's a big but here, that as long as your function has a certain regularity, so this is a Sobolev space, but it essentially means that your function has S derivatives. Okay, S derivatives exist, so the function is sufficiently smooth. Then this is sort of a standard approximation theorem. It goes to Yarotsky, but there are many different variants of it, which says that yes, you can learn this function with a neural network, provided that the number of the error scales like this. So it depends on, this is the number of parameters. So these are these weights and biases put together, the number of parameters, and it scales as the regularity of your function. So the more regular is your function, then the error is going to be smaller for the same number of parameters, or it scales with dimensions. So the less number of dimensions you have, the faster it decays, more number of dimensions you have, the slower it decays. Okay, so this is what it is. But the point is, in scientific computing, often we don't have this kind of regularity. Remember that I am interested in learning things with shocks and so on. So at best, you can expect the function is in bounded variation or something like that. And if you start putting these numbers, even for a moderate dimensional problem, let's say 6 dimensions, but I have only one derivative, then to get 1% error, this kind of a bound tells me that I need a network which is of the size of 1 trillion. Right, this is just incredibly big, right? This is not going to happen. Because what hits us is the curse of dimensionality. Because yes, you can approximate these functions, but the neural network, the size of the neural network blows up exponentially as a function of the dimension. That's why you're hit with the curse of dimensionality. And this analysis tells us that it's a bit more pessimistic in general for functions, if you want worst case guarantees. But the point is that we are not always only approximating functions. We are approximating functions with more structure. These are solutions of PDEs or observables of solutions of PDEs. So can we do something better? And this in a way is sort of the most theoretical slide in a way I have, which is that if you do a little bit more refined work on this, the total error, this is the difference between the neural network and the ground truth, you can break it down into 3 components. Let me walk through each of the components. The first component is what is called the approximation error. It simply tells you that you have a function which is not a neural network, but you want to approximate it by neural networks of a certain size, of a certain architecture, with a certain activation function. what is the best approximation that you can get? Just like in finite elements, what's the best approximation that you can get? And this is where we got this curse of dimensionality, which is very pessimistic. However, if you are smart and realize that this is solutions of PDEs, then there are many results which are available now for elliptic PDEs, parabolic PDEs, even for hyperbolic PDEs. This is a very recent paper where you can prove that indeed this approximation error does not blow up exponentially, but it's polynomial in the dimension. Okay, so this is much, much better that it grows polynomially. In fact, for hyperbolic PDEs, even for hyperbolic PDEs, you can show that it's either linear or quadratic in the dimensions. By elliptic and parabolic, you can do even better. So in principle, you can sort of mitigate the curse of dimensionality and the approximation error can be small. However, that's not enough because in practice, this just tells you that there exists a network with small error. But in practice, you still have to train the neural network and you have to find out whether this, so as a consequence, you have another two components. One is the so-called optimization error, which is related to the training error, which is given here. This is the loss function, which is what you have trained on. Remember that we always have to minimize the loss function. So in practice, this is a very difficult object to, so let's say, constrain theoretically, but empirically, you can determine this because while you're training, you know what your loss function is. So this is a good thing in that sense. And the third bit, which is sometimes hard to bound, is what is called the generalization error. This is the difference between the fact that you have a population risk, an integral, and what is called an empirical risk. Your loss function is what is called an empirical risk or a quadrature. So you have an integral and you have a quadrature. And of course, there is going to be a difference between them, some sort of a quadrature error. And for random points, you can do some statistical learning theory, and you can usually prove a bound, not easily, but with some work, you can prove a bound, which is that this error scales like 1 over square root of the number of samples with a log term. Okay, so the approximation error has to be controlled by the fact that it's a solution of PDEs. Optimization error, you monitor it during the training. And the generalization error, you can get a bound more or less using some form of Monte Carlo, a smarter form of Monte Carlo. And this already is a good story. However, it is still not good enough because what I can say is, okay, let's say that your approximation error is small. You know that you can approximate this function class with a neural network, and you've been able to train your network to high precision. Still, the leading component of the error will be the generalization error, which is written here, and it still behaves like, let's say, order of 1 times square root of n, or worse than square root of n. But let's say it's like square root of n, which is fine. It was far worse before. No curse of dimensionality now. And even if this happens, still to get an error of 1%, if you put this in, you require of the order of 10,000 training samples. And 10,000 is a high number, right? Because remember that each of my samples is 280 node hours. So this is going to be very, very time consuming, expensive, and so on. And here comes the first big challenge, in my opinion, of using machine learning in scientific computing. Because if you think of machine learning, the classical examples, image classification, and so on and so forth, data is very cheap because to get an image is very cheap. However, a lot of our data, what we do, comes from simulations, and these are expensive. So you cannot, so I would say we are in a relatively data poor regime, whereas in the classical applications of machine learning, they're in a data rich regime, a big data regime, right? On the other hand, we also have to learn maps of low regularity. Remember, the better the regularity, the less number of samples I need, the less number of the size of the architecture of the network that I need. So we have to learn maps of low regularity in a data poor regime. And this is a challenge. Let's see what one can do. Well, there are several tricks one can use, and I just present you some of them. The first trick that we can use is, since we're doing simulations, there's no reason why we should use only random points as training data. Okay, fine, random points is a natural choice when in machine learning, but doesn't stop us, right? So in particular, we can choose what are called low discrepancy sequences or equidistributed points. So if you think of it like in terms of how well they cover the space, so for instance, random points are in blue dots. There are many boxes here without a random point. On the other hand, the orange star is a low discrepancy sequence, a snowball sequence, and you see that they are present in almost every box. So by design, these things are sort of equidistributed, well distributed in the domain, and they are the basis of what are called quasi-Monte Carlo integration. So why not use these points? And in fact, this is a very natural idea in this context. And one can prove the following bounds, that as long as your mapping, your ground truth, observable or field, has some bounded variation, some bounded Hardy-Krause variation, then one can prove a result like this, which says that your total error scales. Of course, there is always the training error, which has to be small, but the generalization error scales like 1 over n with a logarithmic term. So this cannot be avoided. 1 over n, remember, earlier I had 1 over square root of n. So this is a big difference. It's between 10,000 and 100. So that makes an enormous difference. You see this in practice also. So there's an example, more artificial example. I'll give you some more examples later, where you can see that the Sobol sequence, the generalization error goes like 1 as predicted. Monte Carlo does a bit better than a half. Here it goes at 0.65. Who knows why, but slightly better than a half, right? Still, there is a significant gap between them. But again, 1 is the limit here. And there is a logarithmic term, which is dimension dependent. So how do you remove that? For that, you need even more better behaved maps. So maps which are essentially analytic, for instance, solutions of elliptic and parabolic PDEs. So in this paper here, we considered the case of such maps. We designed, or we used special of these pseudo-random sequences of quasi-Monte Carlo points, and we were able to show that the error now goes like 1 over n squared, much better than n, much better than square root of n, and there is no dependence on dimension whatsoever, not even a logarithmic term. And you see that also in practice. This is a 16-dimensional elliptic equation and a 32-dimensional elliptic equation, parametric dimensions, and you see that the error is more or less the same. So the point is, if you want even high order convergence, lower generalization error, then you need some properties in the map. If not, it's better to use Sobol sequences. So that's one trick, right? So don't use IID training points, use more fancier or better behaved training points. That's one option. Another option, which is possible because we are doing numerics, is because we can use what is called multi-level or multi-fidelity training. What does it mean? Let me spend a minute to explain this. The point is that, as I said, the training data has to be generated mostly by numerical simulation, and simulations at fine resolutions are expensive. So the more number of training samples you choose at fine resolutions, the more cost you pay in the training. On the other hand, if you had cheaper simulations, like on a coarser grid, then you can do a lot of training samples because this is cheaper. So why not use this fact that our numerical simulations can be done at different mesh resolutions? Not on every problem, but in a lot of problems this can be done. And then use a lot of simulations at the coarse mesh levels and a few simulations at the fine mesh level. This was already done a lot in uncertainty quantification, and you just translate the idea here. So you train not the map at the finest resolution, but what are called details. So the map at the coarsest resolution, the difference between the map at the fine resolution and the coarse resolution, the difference between the map at an even finer resolution and a fine resolution, and so on. People knowing wavelets know this. So if you do that, then as long as the variance of this detail goes down, as it does in many maps, then one can guarantee, one can even prove that this training procedure will give you a significant speed up over single level training. Now, depending on how much the variance decreases, right? So for instance, in this flow past the airfoils, you got a speed up of about 4 to 6 in the interesting region. Not 3 orders of magnitude, but like an order of magnitude, which is not such a bad deal. So together, these two ideas that you can use, let's say, fancier training points, and you can use multi-level training, allows us to do some realistic problems, still at a proof of concept level, but fairly realistic. So for instance, the first example is you have an airfoil. So you use either the Euler or the Navier-Stokes equations. And what you're interested is in predicting either the whole field. For instance, this is the ground truth and this is the density. The parameters now are going to be your shape parameters. So these are a 20-dimensional or 30-dimensional parameter space. And you have 128 training samples, not a lot. The neural networks themselves are not very big. They are between 1,000 and 10,000 parameters. And each sample to generate the training data, the finite volume solver, this takes about 40 minutes approximately. This is a very efficient solver, so it takes about 40 minutes. To train the neural networks, if you want the observables, the lift and the drag, it takes about 10 to 15 minutes, not a lot. If you want the whole field, it takes about an hour, of course, because the whole field is going to be much more expensive to train. On the other hand, the evaluation time, once you have trained, let's say offline, The evaluation time, the online time for the observables is 10 to the power minus 5 seconds. And even for the field is 0.2 seconds. So still about a factor of 10,000 less than what the finite volume solver would have taken. And the errors are very, very low, between 1 and 2%, even for the whole field. So you can learn the whole field to 2% at a execution time, which is 10,000 times less than that of the finite volume solver. So in this case, it really, really works. And it required all these tricks in order to get these kind of results. Here's another example. You can do uncertainty quantification. This is a big problem. And the way you do it is very, very simple. It means you take a bunch of points, snowball points, for instance. And then what you do is that instead of you are interested in the whole measure, not just in the mean and the variance, what you do is you train the surrogate. And remember that this was very, very cheap, right, to execute. So even 10,000, 100,000 samples can be taken very cheaply. And then you form the measure accordingly from the surrogate. So even the training time has to be included now, or the time to generate the training samples has to be included. And you can see for the same problem, we could get the whole histogram of the lift, the PDF of the lift and the drag very accurately. And when you compare with, of course, with Monte Carlo, there is enormous speed up, but Monte Carlo is not state of the art. I would say multi-level quasi Monte Carlo is state of the art. And even over that, we got a factor of about 7 to 9. With single level training, another factor of 5 with multi-level training. So you get a factor of 40 speed up, which is something significant in these contexts, right? It makes a difference between feasibility and infeasibility. Let me give you another example, which is dear to my heart, and people in Milan also work on this problem, which is on PDE constraint optimization. So the interest is design problems are typically like that. You want to design the shape of the airfoil to minimize the drag at constant lift or something like that. And then as you can see, so here is your objective function. There's some cost, and this is the solution of the PDE or the lift or the drag or something like that. And of course, one could argue that take a bunch of points randomly or snowball points, train your neural network. You know it's very, very cheap to execute this or to run it. So why not just use that in a classical optimization algorithm? This might work, but there is a serious obstacle, because remember that your maximizer or optimizer typically lies along a manifold. This is just a cartoon. It lies along a manifold in your parameter space. And this manifold is not well represented if you have a few random or snowball points. These are meant to be equidistributed, right? So this will not work so well. So what we came up here was an active learning algorithm. This paper is already published earlier this year. And what an active learning algorithm does is that you adaptively or actively search for the training set. Instead of a priori fixing a training set, you search for it adaptively. And you can do this in the following manner. I just try to explain it in pictures and words. So you start with a few random points or snowball points in this case. Then you train your neural network. It will be inaccurate, not super accurate representation of your underlying map, but use that inaccurate representation to train a neural network. Once the neural network is there, put it in the optimization problem, and this will spit out your new training points. This will at least supposed to be close to the manifold of training points, and you repeat it. So use the neural network to train or to get the optimizer to work to give you new points, and use those to use the neural network, and do this in an iterative fashion. So there is some multiplicative effect, and one can even prove for convex functions that you get exponential convergence. And this algorithm works very well. And you can see an example here. So you have a reference shape, which is given here in the dotted line here, dashed line, sorry. And these are some optimized shapes. So we reduce the drag by 50%, which is considerable here at constant lift. And the main point is when you try to compare it with another optimizer, for instance, TNC, and we're looking at the number of function evaluations, number of evaluations of lift and drag, but because each of them is a PDE solve, right? Or number of calls to the PDE solve, you can see already with only 60 or 65 calls, we have been able to get a very low value. And the same thing would have taken about 2000 calls, okay, in this particular case. So this gives you a factor of 20, factor of 30, depending on the problem, factor of 10, depending on the problem speed up. And it is only possible because of this adaptive choice or selection of the training set. So these are examples where things work very, very well. However, there are caveats, right? Not everything works. There are caveats. All that I showed you so far, here there was explicit knowledge of the underlying PDEs. I knew that the flow was given by some Euler equations, Navier-Stokes equations, and so on. Moreover, there was because these were design problems or so on, there was an explicit knowledge of the measure, because there is underlying measure on your parameter space, which allowed me to do some parameterization. And I needed a convergent numerical discretization, because otherwise, how would I generate my training data? But in the real world, this is not always true, right? Because many times your physics is either missing or incomplete. There are coefficients in the equations that you don't know. There are source terms that you don't know. The data is rarely given just by numerical simulations, but by experiments, observations. And then this kind of neat procedure doesn't work. And you don't know the measure, the underlying measure well, you only can sample from it. This is maybe you can do IID sampling, but you only can sample from it. Once you put in these caveats, this nice framework that I presented with parametric PDEs and so on, it doesn't really work because you don't have a parameterized PDE. In fact, this is the reason why, for instance, these kind of problems we have not yet been able to do, because, for instance, what you're interested in, these are what are called statistical solutions. So the object of interest is no longer just a function, a mean or a variance. What you have instead is a probability measure on functions. And you have an operator which maps a function space. Just imagine you have initial data, and the mapping takes you to some solution at a given time. So this is really an operator, a mapping between two infinite dimensional spaces. And of course, we can try to parameterize if you know things. If you don't know, we can't parameterize anymore. And in this case, we really have to learn the operator. So this is what happens in what is called operator learning. Operator learning is, in a way, scientific machine learning for scientific computing, because we have operators, infinite dimensional mappings that we need to learn. And in the last year, this has become a very popular field, subfield within scientific machine learning. And one way to do so, which is very powerful, this has been rediscovered by George Kanedakis, who also gave a talk there last semester. I think he told me that. So George proposed this something called depot nets. So this is based on what are called operator networks, which were already there from 1995. So remember, let me just explain a little bit what's going on here. Remember that my object of interest, what I have to learn is an operator, a mapping between an infinite dimensional space, another infinite dimensional space, initial data to a snapshot of the solution at the final time. So the idea is that in these, you have two parallel flows of information. So remember my initial function. So this is the input is a function. So I can't work with a function. I have to approximate it. I have to project it onto finite dimensional spaces. And you, for instance, you can sample it at random points on your domain. This is a possibility, or you can take local averages or whatever. Then you push this through a neural network. This is what is called a branch net. So the input goes through a neural network and it spits out some coefficients. Similarly, the output has to be a function, right? So the final output has to be a function. So given a point in your output space or output domain, what you're interested in is a function. So I have another neural network called a trunk net, because remember the neural networks can approximate any function. So you can use that. So you have a trunk net and you have the coefficients. So think of these as sort of some basis functions for the output space, or some sort of eigenfunctions for the output space. And what you do is you combine them together. So the input is a function and your output is also going to be a function. And you have two neural networks which have to be trained in parallel. So you have data, which is in terms of functions, and you output this, right? So, okay, this seems like a very fancy construction. The question is, why should this be able to learn an infinite dimensional operator by using finite dimensional neural networks at its base, right? And at the same time, you're also sampling a finite number of functions, because otherwise you can't train them. So the point is it can, and this is what was done in this paper, which was put on arXiv very recently. It's a very long paper, almost 112 pages. Unfortunately, we couldn't shorten it. But the point is, depot nets, these deep operator nets, have the same properties of approximation that neural networks, traditional neural networks, had in finite dimensions. So just like in finite dimensions, you could approximate any measurable function with respect to the with the neural network. Here you can approximate any infinite dimensional operator as long as it is measurable with respect to some base measure. So the approximability of these things is guaranteed by this result. Okay, so that's the first thing. But of course, so what? Just like I showed you, there could be a curse of dimensionality, right? And this infinite everything is in infinite dimensions. So one has to define the curse of dimensionality accurately here. And what we were able to prove, this was sort of the hard technical part of the whole thing, was to show that the deponets, they actually break the curse of dimensionality. But this, of course, one has to exemplify. You can't solve every PDE in the same way. But we did a large number of examples. We showed this for ODEs with elliptic PDEs, parabolic PDEs, hyperbolic PDEs, and so on. Let me give you an example of an elliptic PDE. So A is, let's say, the coefficient, rock permeability. U is your pressure. This is a Darcy equation, for instance. The mapping is between A, your coefficient, which is a bounded function, or maybe a smooth function for that matter, to your output, which is going to be also a smooth function. But nevertheless, it's a mapping between functions and functions. So what we're able to prove is that the deponet, these two neural networks together, what we're able to show is that the size is actually subalgebraic. So it's not just linearly growing in the tolerance, error tolerance, it's actually going not just sublinearly, but subalgebraically. So it's really breaks the curse of dimensionality. And it also does the same for hyperbolic PDEs, scalar hyperbolic PDEs, parabolic, and so on. So these are very, very powerful tool to obtain, to approximate operators, not just functions, but really operators. Similarly, one can even prove a generalization error that remember this error between the empirical risk and the population risk that grows as, or that decays as 1 over square root of the number of samples of functions. Okay, so you have to approximate, but still finite number of it. So this is a very, very powerful approximation framework that people have only just now started looking at. So George Kanedakis has many interesting results. We are still sort of getting into the numerics of it, but already one sees some weird phenomena. For instance, at training, one sees often that we prove that it behaves like 1 over square root. But in practice, it trains exponentially fast initially, and then it hits the right asymptotic. So indeed, it's true that asymptotically, you cannot do better than 1 over square root of number of samples, but pre-asymptotically, it goes exponentially down. We have no theoretical understanding of it yet, but this tells you that you can learn things quite fast. And okay, if asymptotically it's 1 over square root of n, who cares? So that this, I think, is a very, very promising future direction. Operator learning in general, deponets is just one framework where one can do a lot of interesting work in scientific computing. So I have about 10 minutes. Alfio, do I have 10 minutes or do I have slightly more time? Hello?
Yes, yes, please go for 10 minutes. Don't worry.
Okay, so let me switch gears, and in the last, let's say roughly 10 minutes, let me also, so all these problems that I described, dependence in dimension was sort of parametric or implicit. What about the problems where the dimensionality is explicit, right? Like I told in the very beginning, your Boltzmann equation, which is 7-dimensional, Black-Scholes, Schrodinger, these are hundreds and thousands of dimensions. So for these kind of problems, you don't even have necessarily even a single solver which is going to handle them even for radiative transfer in 7 dimensions. It's very, very expensive. So you may not even have a single realization will take a lot of time. So this supervised learning algorithms that I presented might not even work. So in this context, I'm going to talk about another more unsupervised learning algorithm that seems to work very well. And these are called physics-informed neural networks. Again, they have been around for quite a while. They were in the 90s. But again, somehow George Kanedakis, he rediscovered them some years back, and he has developed them. And my group, what we have done is we have provided some theoretical basis for this, and we have focused more on the high dimensional problems aspect of it. Let me just quickly go through that. And these are very simple. What are these pins? These are physics-informed neural networks. So let us look at the framework. So you have a PDE. D of u equal to f. D is your differential operator. It could be heat equation, Navier-Stokes, whatever you want. And then the point is your neural network now is a mapping between space and time. So forget parameters for the time being. It's a mapping between space and time and a vector, your output. Okay. So now this is a function of space and time. It's a neural network. It's a smooth function. So you can always evaluate the residual of the PDE pointwise. So you just plug this guy into the PDE. Of course, you are not going to get a 0 because otherwise this would have been the solution of the PDE. But now you can see, okay, why don't I minimize this? Fine, let's minimize this. So let's take some norm and minimize this residual over the whole domain. And of course, you can't work with an integral. We don't know how to evaluate integrals. So you use a quadrature. And this quadrature is exactly what is related with the training error, the loss function. So a pin is nothing but a neural network which simply minimizes the residual of the PDE and some other things. But and why should this work? Means why should residual minimization work? So it works as long as your PDE is stable. And this is a main theorem in this paper, that we leverage the stability of PDEs. So what is the stability? Stability is simply that if I change my output, remember du equal to f. So if I change my input, there is a proportionate change in the output. Of course, the constants, because these are nonlinear problems, they could in principle depend on your solution. So this is what is called conditional stability. Once you have this, then one can show error bounds on pins. And this takes exactly 2 lines. So let me try to explain it. So error is simply the difference between your pin and your exact solution. Fine, and some norm, natural norm here. And then, of course, remember that my PDE or differential operator is stable. So I just substitute this here. So this is the stability. But remember that u is my exact solution. So I can replace d of u by f. So I'm back here. Now, what is d of u minus f? That is precisely my residual evaluated at the training point where I have already trained. So this is nothing but your residual star, which is sort of the minimizer. So this comes here. And of course, this is a integral. I need to approximate with quadrature. So this is your training error. This is what you have already computed. This is some quadrature error, which you can control if you have sufficient number of quadrature points. You can use Monte Carlo, you can use quasi Monte Carlo, you can use, for low dimensions, you can use a lot of fancy things here. And then you have got an error estimate. So you have simply leveraged the stability. If your PDE is stable, if these constants are bounded, and if your training error is low, and if you have enough quadrature points, then a pin is a good approximation to your PDE. That's as simple as that. And of course, in each individual case, you have to check this, but the program is essentially there. And of course, this can be, let me illustrate this with a very simple example, just the heat equation in one space dimension to begin with. So what is a pin? Remember, there's a heat equation. What I do is I also have boundary conditions. I have initial conditions. In this case, I just take 0 Dirichlet boundary conditions. I put some, this is time here, this is space. So I put some points in the interior. These are, I think, random points or Sobol points. I don't remember now. These are some other points here in the boundary on both spatial and temporal boundaries. Then you just put the residual at these points and you minimize the residual, the mismatch in the boundary points, and the mismatch in the interior points. So these are the parameters of your network. You simply minimize this. And then by following the stability program, this is a linear PDE, so this is straightforward, you get an error estimate of this form. Okay, and this can be done, nothing stops you in one space dimension. You can do this in 100 space dimensions. Heat equation is a nice equation, so you can do this. Let me be a bit quick here. So it can be done in a lot of space dimensions. You see 20, 50, 100 space dimensions, and the error grows linearly, if at all. If you fix the training time, then the error is growing linearly. So you don't have a curse of dimensionality. And this is also proved in a forthcoming paper. So pins are really powerful for high dimensional problems. So why stop at the heat equation? The common high dimensional problems are problems coming from finance, like Black-Scholes PDEs, Heston PDEs. In each of these cases, you don't give any information other than the residual. And each time you see that the error, even in 100 dimensions, is like 1.8%, 1.5%, and so on. And the training time in 100 dimensions is approximately 50 minutes. So you solve this in about 45 to 50 minutes. So it's not a huge training time, but it's not like 1 minute. It's a 100 dimensional problem. So you can't expect to solve this in 1 minute either. So this is a very powerful way of solving without any additional knowledge, because people can always use a Feynman-Cox formula. But if you don't use this, then this is a good way to do things. And let me do a more physics equation, right? Because, okay, finance and so on. Personally, I'm more interested in the physics set of equations. It's a very common equation that crops up in physics all the time, radiative transfer. So U is the radiative intensity. It's a function of space, could be 3 dimensions, angle, omega, 2 dimensions, frequency, nu, which is a scalar, so 1 more dimension, and time. So it can be a 7-dimensional problem. It has a hyperbolic structure because you have transport, but you also have some non-locality because of the scattering kernel. And you could have some multi-scale or multi-physics behavior, because if you have a very transparent medium or a very opaque medium, it can go between parabolic and hyperbolic. Now, PINS provides you a beautiful way to approximate this, because it doesn't require any data. It's free of the curse of dimensionality. And you can see some examples here. So this is two-dimensional, one space and one angle. There's even a discontinuity. It approximated it very well. Of course, the error was 0.3%, but here I fixed the training time to be 1 hour. Okay, what's the big deal? You're solving a two-dimensional problem in one hour. But the point is the next one, because here it's a 6-dimensional problem. The error is now 2% roughly. And this is what this is the incident radiation, this is the radiative flux. And again, it's roughly 1 hour. You get 2% error in 1 hour. And this is not possible with finite elements and the other state-of-the-art methods that are there. So it's a very powerful tool for these kind of problems. Let me hurry up a bit. I want to wind up in 5 more minutes. So this was with radiative transfer equations. You can do this for nonlinear dispersive PDEs. But of course, not everything works with PINS. So it's also important to highlight the limitation. So one limitation, for instance, could be done if you take viscous-Burgers equation, right? So just in one space dimension. So nu is your viscosity. And one can follow this program and one can prove these error estimates. But the point is that in the error estimates already, you see that they will blow up with 1 over the square root of your viscosity. So if you have shocks, for instance, then this shouldn't work. If you have rarefactions, it should work. And this indeed happens. PINS works excellently for rarefactions. But as soon as you have shocks, you have loss of regularity and things blow up, then you cannot do this anymore. And you also see that in the numerics. So of course, it's very natural to, instead of looking at a strong form of the residual, look at a weak form of the residual. This is very recent work. It's not even finished. But the point is now, of course, you don't just have the function, your solution, you also have test functions. And you have to maximize, these are also neural networks. You have to maximize over them. You have to minimize over your test functions. And you have to train these together. So this is what is common in adversarial training, or generative adversarial networks. And already the first results are very positive. So remember, we had like 20% error. Now it is roughly 2.5% error. So you, in a way, you solve this problem. But of course, it's very expensive. So I'm not sure how much one can push it and whether one can even do these kind of problems where there's a loss of regularity with PINS. But on a positive note, what PINS are very, very good at is inverse problems. Because inverse problems, you have some data, but you may not have the whole physics. Or for instance, this is a data assimilation problem. You have a Stokes flow. You know that you have a Stokes flow in the whole domain, but you don't know the boundary conditions. You only know the value of the density in some points in a part of the domain, what is called the observation domain. So PINS are trivial to implement because you put the PDE residual and you know some data, you just append that to the residual and then just minimize everything. Okay, just minimize everything. One can use some deep mathematics, in this case, Kalman estimates, and prove that indeed this will work. So in this case, you can actually prove that this will work. And you see that in practice. George has used this for Navier-Stokes and so on. We don't have proofs for Navier-Stokes, but for Stokes, for instance, we have proofs. And you can see that the ground truth and the PIN, they almost agree with each other. And even for the pressure, because for the pressure, we have no measurement whatsoever. But as you can see, with very few points, this is like 1 minute computation, you get 3.5% error. You can go further if you want. So let me just wind up with a final inverse problem. So radiative transfer, remember that often, and yesterday I was talking with some physicists who are interested in exoplanets and detecting the atmosphere of exoplanets. So you don't know, you have some measurements of the radiation, some incident radiation or something like that, but you don't know that absorption coefficient, you don't know the scattering coefficient and so on. So how are you going to use that? Remember, just append the data with the PDE. And here, for instance, we are able to solve a 5-dimensional radiative transfer inverse problem to about 2.5% error in 1.5 hours. It's not cheap, but it can be done. Inverse problem, because of course a direct problem you can solve it in 1.5 hours, but to solve the whole inverse problem as a single shot, this gives you a lot of advantages. So I think with this I will just summarize. So I wanted to show you some research in my group, at least, on deep learning and high dimensional PDEs. And we covered 2 classes of problems, I would say. Many query problems, these are parametric PDEs. where we were able to do prediction, we were able to do uncertainty quantification, PDE constraint optimization. I get a very small glimpse of operator learning. This is going to be the future, in my opinion, and how deep nets work in that. And for other problems, you have pins. They're a very powerful tool for high dimensional forward problems and for inverse problems. And there's a lot of activity on also in Alfio's group on use of deep learning in scientific computing. I only presented a very narrow sliver of what's going on. But the message is that successful application requires significant innovation over black box machine learning algorithms. None of the results that I showed you would have been possible just by taking PyTorch and just running a convolutional neural network through it. Then you would not get the sort of results we got. Anyway, I thank you very much for your attention, and my apologies for taking slightly longer than I expected. Thank you. I'll be happy to take questions, but I don't hear anyone.
I'm muted.
Oh.
Okay, that's fine. I was muted by the organizers. So thank you very much for this really fantastic talk. This is indeed a kind of encyclopedic research work, and we open the avenue to many different developments. I just want to start with a very tiny question. When you use your say DeepNet kind of approach, namely the way you want to learn the PDE, you mentioned a couple of times that you're actually needing in your estimates the stability, to have stability of the PDE. I'm wondering if you need the stability of the PDE or if you also need the stability of the numerical approximation that generates the data of the PDEs.
No, actually, Alfio, there are two questions in a way. First, stability was important for pins, not for DeepNets. So here you needed stability.
Yes, okay. All right.
So here you needed stability. Here there is no numerical method whatsoever. This is the numerical method, right? Because here I don't need any data except the initial conditions and the boundary conditions.
All right, then you need the stability for the PDE.
So I need the stability. Here, on the other hand, I don't, in a way it is built, there is no numerics anymore. There is no numerical operator whatsoever. In principle, you can give me noisy data from experiments or whatever here, and it doesn't have anything to do with numerical schemes. However, in some of these problems, all that we have done in a way is to emulate the action. If you if you look at a high level, these are nothing but a fancy way of doing, or the worst case, they're a fancy way of doing finite elements or finite differences. At the worst case, of course, when you train, they probably do something much better. But many of the theorems are proved using the fact that we can emulate numerical methods. Right, so this is, in a way, it's a good question, because if I did not have a stable numerical method, for instance, the conservation law, it's based on a stable numerical method. So all that I prove is that without knowing that only from this operator, there exists at least one DeepNet which emulates the numerical scheme, which has these properties. Of course, during training, it can do much, much better, right? But these are worst case guarantees. So inbuilt, there is some stability for your numerical method. But these problems, for instance, we did not use the numerical method at all. These are because there is some analyticity. So once you have some analyticity, you just use that, right? And then that's why you get this super nice convergence. But indeed, at the moment, some problems you can prove that you don't care about numerical methods at all. But many problems, what we implicitly do is emulate numerical methods. So this is just a valid point.
Thank you.
There is a question by, please unmute yourself, and I don't know how the organizers want to do the question Q&A. You can also ask in chat. I'm able to see things in chat.
Okay, so hi, I'm Nicola. Can you hear me?
Yes,
can I make a question?
Yes, for sure.
Thank you very much, Professor Mishra, for the truly interesting talk. And I just wanted to ask you something about a comment or an opinion on the structure of DeepNets. So
yeah,
maybe it's easier to understand if you go back to the slide where there is the definition of a DeepNet.
Yeah, I was, maybe I tried to cover too much, so I was not very, let's see, why is it not working? I should do a full screen, sorry. Yes, no, yeah. Tell me.
Okay, so in principle, if I'm understanding correctly, the trunk nets are in a way providing a basis on the output space of the operator. Is that correct? Okay.
This is absolutely correct.
So in the case I have high fidelity samples coming from numerical schemes, which I would like to use as training samples, my first idea would be to find the basis using methods such as projections, or I have my training samples and maybe I do some PCA or some kind of, where is the advantage in using networks to represent this kind of basis?
So the beauty of this is that it learns that, right? So you don't, indeed, what you can do and what we proved also in the paper is that in principle, there are several of these. So this step here, which we call reconstruction, it's almost entirely tied to the eigenstructure of your operators somehow. So you have some initial measure, and you have the push forward measure with respect to your operator, and then this, of course, is a nice operator in the sense that I can define its covariance operator and so on. And then what we proved is DeepONets certainly can learn the PCA by itself. And maybe it can do even better. If it can learn the PCA by itself, it can do even better. So you don't have to provide any information to it. It should learn. But of course, if you have additional information, possibly, yes, you can beat it, right? Because in principle, I could have just used a PCA here and I could have used a PCA here. People have done that. Andy Stewart, for instance, in Caltech, he has done that. But DeepONets don't need that information. And you're only able to do that because you know your problem well, right? So in the sense that you know what is your input measure and what is your output measure, so you can do, or you can do an empirical PCA. But the point about DeepONet is that it can do it by itself. And the proof actually uses the fact that it somehow learns PCA by itself on the fly. But it could happen that if you already know the PCA, or you have a very good basis for the output space, why do I use this, right? There are two arguments for it. A, maybe it will learn something better than what our a priori choice is, because the proof says that at worst case, it will behave like that, right? B, maybe in some problems, you don't have that kind of information. So the only reason why you have high fidelity numerical simulations is because you know the physics well, right? Suppose you did not know the physics well for some particular problem, then you wouldn't have a high fidelity numerical simulation. This is a completely black box approach to do the same thing, but you're right. If you have additional structure, then why not use that? But if you don't have additional structure, it makes, what we prove is that it actually learns that structure by itself.
Okay, I do understand. And the fact is that this structure is mesh-free, in fact.
Completely mesh-free.
As the other approaches, as I understand, right?
This
also
is completely,
the previous. The other networks you have shown are also mesh-free. Okay.
Everything is mesh-free here. So there is nothing which is mesh-free. Pins is also mesh-free and so on. Of course, it's not always, this is hard work actually, because here you could have potentially thought of a mesh, right? Because you are taking a function and you're sampling it. But if I do it on a grid for nice functions, then things become easier. But the hard part of our paper, which is another 10-20 pages to it, is that even if I do it random points, which is the best I can do, right? I can just take random points, and if I don't know anything, I do random points. Then we actually prove that this is near optimal. So it's optimal up to a log. Okay. So you don't need any information. That was a hard part. That's why the paper is sort of long in that sense. So thank you, but this was a very, very good question. It is indeed a valid point.
Thank you very much.
Is there?
Are there other questions?
Yes, there is a question by Salvatore. There's a question by Lorenzo.
Yes,
of course.
Salvatore,
there are questions. So Salvatore, his question is, how difficult is it to construct a good training set? Again, it depends on, and he's actually asking about the inverse problem, right? Oh, sorry. Let me, again, since I mixed various things, people are naturally a bit confused. So Salvatore, for your question, for this, I presume you are asking about this problem, right? Here, the training set is just the data, I think if I remember correctly, it was some data points. It was not chosen with any particular care. It was simply done by taking some random data points. Here, as you can see, the training set was, here it was also based on some radial points here. So there is no, in these problems, for inverse problems, you should not be too specific about the choice of your data set, right? Because inverse problems means that someone else gives me the data and I give them a solution. So you cannot be too demanding. And indeed, you're not demanding at all here. So random points are good enough, okay? Whereas for the earlier ones, in fact, one of my main message for the forward problem was to find good training points, right? Use, for instance, Sobol points or adaptive points or something like that. Because if you have more information, like Nicola asked last question, if you have more information, then why do I stop at random points? I can take, for instance, Sobol points, grid points, whatever. Means it depends on, of course, grid points are not very useful for very high dimensions. But so indeed, there are two aspects here, which I probably did not differentiate that well. My apologies. Lorenzo, you have a question. How are you doing?
Hey, hi. Good.
Hi,
Good.
Lorenzo.
What about
How are you doing?
How's everything? Yeah, well, given the circumstances, doing fine. Yeah. Well, so thanks for the talk. And of course, my question is on the first part of the talk, so on the parametric PDE side. So you showed us this example of the lift and drag, where you show that you got like a 15 times factor improvement in the shock problem, right? Yeah, here.
Yeah.
So yes, exactly. So
probably this one. I'm sorry. Probably this one you meant. No.
Yes. So let's say you said multi-level quasi Monte Carlo is the state of the art, and you.
In my opinion, yeah, maybe.
Yeah,
so.
well, I totally agree with that. I just wanted to know if you have the same feeling that the same thing happens also for regular parametric PDEs problems, because you know that the shock problem is a problem where the old methods are not well performing, right? But for instance, in the elliptic PDEs, the Darcy problem, there's a lot of stuff that has been developed in the last 10, 15 years, right? So component sensing and polynomial chaos and whatever.
This is a very very good question. As you know very well, I'm more on the hyperbolic side of the side of the divide. What I know is I, of course, talk to elliptic people, and I know I have spoken a lot to Wolfgang Dahmen because he tried to do some of these things for elliptic problems. And he said that he could beat the performance of deep neural networks with much simpler model order reduction things. So clearly for elliptic problems, it is probably not the best choice. You know, because it's a sort of a linear problem. It's probably not the best choice for elliptic problems, for the pure elliptic problems, right? Not a lot of complications.
Yeah, because the map from the parameters to the solution is analytic, right? So,
yes, but of course, also on the neural network side, you can use that. This is what Christoph Schwab
uses because you had,
time, right?
yes, exactly.
And so I don't know. I personally have not done any numerics, so I cannot say. But I see that there is I in fact use that analyticity for my depot nets. Okay, so for the depot nets, I used analyticity heavily, and that's why the elliptic problem, it was sort of going very fast. But of course, the classical methods are also very good. So it's
Then of course it's always good to see what the new things do on the old problems and see what happens. So it is by no means a critique, right? It's just if you have an idea or
my feeling is that it is not a clear winner, because in these problems it is a clear winner because
I agree.
You see why, right? The structure is because for a neural network to learn this is very easy, whereas to learn this is very easy for a neural network. You know, it's a very easy thing, but for a classical sort of linear model order reduction, this is almost impossible. So this is why there's a big difference. It's a very good choice in a way to look at hyperbolic problems, right?
Yeah, it's always good to have more methods than less, right?
Yes, and for elliptic problems, I'm not completely convinced. Let's put it that this is the best choice.
Yeah. Okay. Thank you.
On the other hand, for inverse problems, this is particularly then for inverse problems, if you have things like pins and so on. For elliptic problems, pins also work very well. And then if you can do inverse problems at one shot, why not do it, right?
Yeah, sure, of course.
Thanks.
Okay,
good. There is a question by Stefano, and there's also a question by Ricardo in the chat. So who should I go? I don't know. One of you go first randomly. Maybe Stefano can go first.
So I'll go first.
Yeah.
So thank you, Professor, for the talk. I have a question about the loss function. In several examples, you show that the loss function is sum of different components.
Yeah.
And my question is related about the possibility of weighting these components. So the effect of using some constant or some weights, some specific weights, in order to maybe improve the performance in terms of accuracy and also in terms of training time.
This is a very, very good question. Actually, if you, we have tried this. Let me give you the one where I actually have it on the slides, right? This is the easiest. So right here, where is the pins? So right here, as you can see, so the loss function for if you choose IID, or if you choose like Sobol or some quasi-random sequence, then of course there is no weightage whatsoever, right? Because these are randomly chosen or quasi-randomly chosen. So why would you care? But for instance, here already, this is in principle, we allow for quadrature points, right? So quadrature points, for instance, correspond to Gauss quadrature, whatever, Klintz or Curtis, whatever. Then of course, this quadrature error is much, if the loss function or in this case, the residual has a much better, let's say, regularity, then indeed this will give you better results. So this is heavily used, but this is only valid for low dimensional problems, right? If you have 1, 2, 3 dimensions, then it's possible. If you have a 10-dimensional problem, then you can't really use more regular quadratures, but you can use adaptive quadratures, right? You can use what adaptive quadratures. This has also been experimented in my group, again in the airfoil case, and it has led to better performance for sure. So this is definitely a possibility. This has already been. So think of this loss function as nothing but a quadrature for the underlying population risk. And you can be very inventive with respect to how you do quadratures, right? But then you need to know also the smoothness of the underlying map, which is not always there. So indeed, this can very much be done. And this has been done, for instance, here.
Okay, thank you very much.
And then there's a question by Ricardo. He says, how do you get the ideal neural network architecture for a given problem? I wish I knew that, right? Means this is a very, very difficult question and a very good question. Then you need to know a lot about your problems, and also you need to know a lot about neural networks, right? So even then, this is not good enough. Let me give you a concrete example, perhaps. Let's go to the airfoil example, because this is the easiest to communicate. So how do we set this up? We know that Sobol points are going to do better than random points. So my training data is chosen by Sobol points, maybe with some multi-level or something like that. Fine. But still, what about the loss function, for instance, right? What about the activation function? ReLU is fine, TANH is fine, but who knows who is the better one of these two? Now, about the architecture of your network, means how many layers do I need? How many neurons per layer? This depends a bit on the problem that you have, right? Because if you take a very deep architecture, then you also need enough training samples to feed it. It's longer to train, longer to execute, right? So what in my group, what we do is what we simply call ensemble training. And everyone in machine learning does this, that you a priori fix some architectures. Like let's say that I look at 4 layers with 40 neurons, 8 layers with 20 neurons, right? And then I do an ensemble training. I have some validation set or training set, and I see for what architecture I get the lowest loss on the training set, right? And then based on that, also for what activation function, what sort of loss function. So there is, this is a problem dependent feature, means you cannot, and most of all, you know that the optimization problem is a high dimensional, very high dimensional, non-convex. Even for the small problems, you have 10,000 parameters. So you're solving a non-convex problem, optimization problem in 10,000 dimensions. So you can imagine how expensive or how, let's say, stochastic almost it can be. You're also using a stochastic gradient method. So different starting points of the weights and biases can lead to very, very different answers. Okay. Is that good? I am sorry, my kids are crying in the background. If you hear that.
Yes, Ricardo said that is perfect.
Okay.
Are there other questions from the audience for Siddhartha Mishra? Okay, if not,
Okay.
I'd like
Thank
to
you very much for your time, and it was a pleasure to talk to all. Yeah, as he said, there is a recording also. Okay, thank you so much, Luca and Christian, and also say bye-bye to Alfio, who had to leave.
Yes,
but,
of course.
Thank you very much.
Thank you for this very interesting and innovative talk, and
bye-bye.
see you next time. Thank you very much. Bye-bye to everybody.